Welcome back. This will be the second installment of our video lectures on section 1.2. We're covering length and angle, the dot product. In our first installment, we did the dot product, length, and distance. In this installment, we'll look at angle, orthogonality, and projections. So let's begin with angle. And a good way to get started thinking about angle is to think about the following scenario. So imagine that you've got a pair of vectors in the plane, u and v, and let's think about the included angle. So let's call that angle theta. We want to know how to calculate the value of this angle theta, and a good way to get started on that is to think about the triangle that's implied by u and v. So let's consider the triangle with sides u and v minus u. We can apply the law of cosines to this triangle and work out this angle theta. So let's look at the statement of the problem. Let u and v be non-zero vectors in R2 and let theta be the angle between them. Apply the law of cosines to the triangle with sides u, v, and v minus u, and show that the dot product of u and v is equal to the length of u times the length of v times the cosine of that included angle. Now, that's equivalent by solving for cosine of theta. That's equivalent to saying that the cosine of theta is equal to u dot v divided by the length of u times the length of v. Now, both of these formulas are important because this formula gives us another way of thinking about what the dot product is. It says I can always think about the dot product of u and v as the length of u times the length of v times the cosine of the included angle. And this formula allows me to think, how could I calculate this included angle? How could I get a handle on the angle theta? And the left-hand side tells us that we can always get it by calculating the dot product of u and v divided by the length of u and the length of v. So both of these formulas are important. Let's go to the document camera and apply the law of cosines and see how these formulas come out quite naturally. Okay, welcome to the document camera. We're going to apply the law of cosines to our triangle and work out this formula for the cosine of the angle between the vectors. Let's just kind of draw our picture again so we can have a reference. So in this case, we've got a vector, a pair of vectors, which we will label u and v. And we'll look at this vector, this third vector, v minus u. Okay, and this gives us a triangle, and we'll call the angle between the vectors u and v, we'll call that angle theta. Now, the law of cosines, in some sense, is an extension of the Pythagorean theorem, and it lets us write the square of the length of this side in terms of the squares of the length of these other two sides, and the cosine of the included angle. So here's what the law of cosines would look like in this case. So it would say that the square of the length of this side would be the square of that side, square of the length of that side, plus the square of the length of the other side, minus 2 times the product of their lengths, times the cosine of the included angle. So that's a statement of the law of cosines. Now what I want to do is work on this side a little bit. Let's do a little side calculation. Right, we know anytime we see the length of a vector squared, we can always reinterpret that as a dot product, right? So we can think of the length of v minus u squared as v minus u dotted with v minus u. It's a very helpful idea. And now we can use our distributive laws to work this out as v dot v minus v dot u minus u dot v minus plus u dot u. Now let's use our commutative law. Let's flip this one, write this one as u dot v. And at the same time, we'll reinterpret these as lengths squared. So this can be written as length of v squared minus 2 u dot v. That takes care of those two middle terms, and this is going to be the length of u squared. All right, now let's bring that back into our main calculation and replace that on this left-hand side. So on this left-hand side, we can now have length of v squared minus 2 u dot v plus length of u squared. All right, that's on the left-hand side. On the right-hand side, we still have this. Now let's see what kind of cancellation ensues. We have a length of v squared on this side and a length of v squared on this side, so we can cancel those from both sides. We've got a length of u squared on this side and a length of u squared on this side. And cancel those. Let's take a look at where we are. All right, at this point we can see that we have a common -2 multiplying both sides, so we can cancel that out. And so we come to the final conclusion here that u dot v can be expressed as length of u times length of v times the cosine of the angle, the included angle between the vectors u and v. That's one way of expressing our results, so let's kind of make note of that. This allows us to interpret a dot product in terms of this included angle. And the other way of interpreting this is to solve this for the cosine of theta, so that we can imagine calculating the cosine of theta in terms of this dot product. So the other interpretation that we'll want to carry with us is that the cosine of the angle between this pair of vectors can be expressed as the dot product times the length of u and the length of v. So there's another interpretation. So this one allows us to reinterpret the dot product in terms of a geometric. This gives us a geometric interpretation of the dot product, and this allows us to think about how we could calculate the angle between the vectors in terms of dot products and lengths of vectors. Okay, so that let's head back to the course notes and continue on. Now, based on our work with the vectors in the plane in R2, it makes sense to make the following definition for the angle between two vectors in general. So for non-zero vectors u and v in Rn, the angle between u and v satisfies the equation cosine of theta equals u dot v divided by the length of u times the length of v. So this is going to be our definition of the cosine of the angle between vectors in arbitrary Rn's. Now, to get a feel for this, let's work out this problem, right? So let's find the angle between a pair of vectors, in this case, two vectors in R5. So join me at the document camera to work out the details of this problem. All right, welcome back to the document camera. We're going to want to work out the angle between the vectors u and v. I've just taken the liberty of writing these vectors here already for us to save us a little bit of time. Now, to calculate the angle between these two vectors, we're going to use this result that says the cosine of the angle can be written in terms of the dot product of u and v and the lengths of u and v. So we've got a few calculations to do. Let's work out the dot product first. The dot product is simply what we're going to get by component-wise multiplication and then addition. So we're going to get a 1, a 0, a 0, a 0, and a -4. So the dot product is simply going to be -3. Now to get the length of u, we're just going to sum the squares of the components and take the square root. So we're going to get a 1, a 0, a 4, a 16, and a 4. That's going to be 25, and the square root of 25 is 5. The length of v, 1, 4, 0, 0, and 4. That's going to be 9. And so the length of v is simply 3. Now, we know that the cosine of the angle between the vectors is going to be u dot v divided by length of u, length of v. So plugging in, we'll have negative 3, we'll have 5, and 3. Well, the 3's cancel, so we get negative 1/5 or negative 0.2. Now, at this point, this is not a common value for the cosine. This is not going to be an elementary angle. And so we would have to use some kind of device to help us calculate this. So I just plug this into the calculator. I use the inverse cosine function. And theta in degrees comes out to be about 101.5 degrees, or in radians, about 1.77 radians. So whether you wanted to express the answer in degrees or if you want to express the answer in radians, either way is fine. But this last step, we would just have to use a calculator to help us finish up the problem. The main thing, though, is to understand how the cosine of the angle is related to these, in this case, the dot product and the lengths of the vectors. And so we can get a simple answer for the cosine and then invert that. All right, let's head back to the class notes. All right, let's put all of our theory to work here. In this problem, we're going to let u and v be vectors in Rn with lengths 4 and 5 respectively. The angle between the vectors is 60 degrees. We want to find the length of the vector 3u minus 4v. Now, let's head over to the document camera and put all the pieces together and find the length of this vector. But this might be a good time for you to pause the video and think about what you would do. All right, so I'll meet you over at the document camera. All right, welcome to the camera. Let's take a look at this problem. We want to find the length of the vector 3u minus 4v. So this is our goal. We're going to try to find the length of 3u minus 4v. Now it turns out the first key insight is it's actually much easier to find the length of this vector squared. And the reason is because we have a way of expressing the length of a vector squared in terms of the dot product. Now, what we can do is work out this dot product, use the distributive laws to work out this dot product and get this dot product expressed in terms of things like u dot u, v dot v, and u dot v. So let's work out this dot product. So we're going to have a 9u dot u. We'll have a minus 12 u dotted with v. We'll have a minus 12 v dotted with u. And we'll have a 16 v dotted with v. Okay, now let's clean this up a little bit. We know that u dot u is just the length of u squared. We know that by the commutative law that v dot u and u dot v are the same thing, so we can think of this as a single minus 24 u dot v. And then this can be expressed as 16 times the length of v squared. Okay, now we know what the length of u is. That's going to be the 4. We know what the length of v is 5. So in some sense, these parts are known to us. This is the part we have to work on still. Now, we don't have explicit components for our vectors u and v, but we do know that the angle between them is 60 degrees. So we can work out u dot v just knowing the lengths of the vectors and the angle between them. So let's do a little side calculation here. So we know that u dot v can be expressed as the length of u, the length of v, and the cosine of the angle between them, which is given to us as 60 degrees. Okay, now we know the length of u is 4, the length of v is 5, and we know that the cosine of 60 degrees, that's one of the elementary angles, that's going to give us a cosine of 1/2. And so u dot v is equal to 10. So let's go back up into our main calculation and start substituting. We've got 9 times 4 squared. We've got minus 24 times 10, which we just computed down here. And then we've got 16 times 5 squared. Okay, so that's going to be 9 times 16 minus 240 plus 16 times 25. Now, 9 times 16 is going to give us 144 minus 240. And 16 times 25 is going to be 400. And so when I finish this calculation, I'm going to get a grand total of 304. Now we have to be a little careful here. Remember, we started with the length squared is 304. So our final answer is going to be the square root of this. So finally, the length of 3u minus 4v is the square root of 304, which is approximately 17.43. Okay, so we can approximate the length of 3u minus 4v at about 17.43. Strictly speaking, it's the square root of 304, approximately 17.43. So this is a wonderful problem because it allows us to basically take a vector, a linear combination of u and v, and just knowing some information about u and v and their lengths and the angle between them, we can work this out. Okay, so this kind of reinforces how all of our theory can be brought to bear on a problem like this. So I hope you enjoyed that solution. Let's head back to the class notes and continue. Our next subsection is entitled orthogonality, and I want to begin by showing you a picture of orthogonality. So when we think of orthogonal vectors, we should have a picture like this in mind. U and V are at a right angle to each other. So orthogonal is just a fancy word for at a right angle to. That means that the angle between u and v is either, we can think of it as 90 degrees or pi over 2, but no matter whether we think of it measured in degrees or radians, the important thing is the cosine of the angle between u and v must be equal to 0. Now, if you track that down, that means that the dot product of u and v must be equal to 0. And this, in effect, becomes our defining property for orthogonal. Two vectors u and v in Rn are orthogonal or at a right angle to each other, provided that u dot v is equal to 0. So we can easily test whether a pair of vectors is orthogonal just by checking their dot product. If the dot product is 0, they're orthogonal. If the dot product is something other than 0, they're not orthogonal. Now we can tack on one additional concept while we're here. Two vectors in Rn are called orthonormal, provided that they are orthogonal and each is a unit vector. So not only would they have to satisfy this condition that u dot v is equal to 0, but each would have to be a unit vector or a vector of length 1 in its own right. Now, let's work a problem that uses both of these concepts, orthogonal and orthonormal. Let's show that the standard unit vectors in Rn are pairwise orthonormal. So join me at the document camera to work out the solution to this problem. Welcome back to the document camera. In this problem, we want to simply show that the standard unit vectors in Rn are what are called pairwise orthonormal. That means that if I take any two of them, they each have length 1 and they're orthogonal to each other. Now, this can get a little cumbersome in terms of the notation if I try to do this in general. So let me just show this to you in R3. So we'll look at the three standard unit vectors in R3 and we'll show that they each have length 1. And if I take any pair of them, they're orthogonal to each other. So let's write out our standard unit vectors. So in R3, there's going to be 3 of them, namely E1, E2, and E3. In other words, the subscript just tells us where the 1 is and the other components are equal to 0. Now, clearly, Each one of these vectors has length 1 because when I take the sum of the components squared and add them up, I'm always going to get 1, and the square root of 1 is 1. So they each have length 1. And that's part of being orthonormal. That's the normal part of being orthonormal. Now we have to show that if I take any two of them in pairs, that their dot product is equal to 0. Now there's going to be 3 different ways to take them in pairs. So if I look at E1 and dot it with E2, you can see that when I do the pairwise multiplication, I'm always going to get 0. So E1 dot E2 is going to be 0 plus 0 plus 0 or 0. When I take E1 dot it with E3, again, when I compare these two, I'm always going to get zeros when I do the component-wise multiplication. So again, I'll have 0 plus 0 plus 0 or 0. And then the last pair is E2 and E3. And once again, when I compare them component-wise, I'm going to get 0. Okay, so this is the orthogonal part of the argument. This shows that they're pairwise orthogonal. This calculation that we did at the beginning shows that they each have length 1, and so together that shows that these form a pairwise orthonormal system. Let's head back to the class notes. Now let's take a look at a theorem that's probably very familiar to you, but we're going to look at it in its vector form, and this is Pythagoras' theorem. So for all vectors u and v in Rn, the length of u plus v squared is equal to the length of u squared plus the length of v squared if and only if u and v are orthogonal. Now, we have to pay, we'll go to the document camera and work this out, but we have to pay special attention to the fact that this is an if and only if statement. So there will be 2 things that we'll have to show. We'll have to show that if the vectors u and v satisfy this condition, then they're orthogonal. And we'll have to show that if u and v are orthogonal, then they satisfy this condition. So let's go to the document camera and work out the details of Pythagoras' theorem. Welcome back to the document camera. Now, before we get started in earnest on proving these implications, I want to do a calculation that I'm going to use in both halves of the proof. And we're going to start by working out the length of u plus v squared. Now remember, I'm going to do a little calculation down here. A little side calculation here. Now remember, anytime I'm working on a length of a vector squared, I can always interpret that as a dot product. So let's take a look at this. The length of u plus v squared can be thought of as u plus v dotted with u plus v. Now, we can work this out using the distributive law. We're going to have u dot u. We'll have u dot v. We'll have v dot u. And finally, v dot v. Now we can interpret u dot u as the length of u squared. I'm going to use the commutative law here to write these as 2u dot v. And then finally, this is just the length of v squared. Okay, so what I'm going to do is I'm going to rewrite this formula by bringing the length of u squared to the other side and the length of v squared to the other side. So here's my master formula that I want to have in place before I start the proof of this. I want to make note of the fact that the length of u plus v squared minus the length of u squared minus the length of v squared is equal to 2 times the dot product of u and v. Okay, so this is something that's always true. All right, always true. Now let's see how we can use this to help us prove the two halves of this theorem. All right. So in this first half, in this direction, we're assuming that this is true. And from the truth of this, we want to conclude that u and v are orthogonal. All right. So if this is true, so if u plus v squared is equal to the length of u squared plus the length of v squared, then the length of u plus v squared minus the length of u squared minus the length of v squared is equal to 0 by just bringing these two pieces to the other side. But this implies, according to our master formula, if this is equal to 0, this implies that 2 times u dot v is equal to 0. Or after dividing by 2, u dot v is equal to 0. But this is precisely what it means to say that u and v are orthogonal. And that's the conclusion of the first half of the proof. If this is true, then these vectors must have a dot product equal to 0, and that means they're orthogonal. Now let's assume that these vectors are orthogonal. So if u and v are orthogonal, then that means that their dot product is equal to 0. Thus, according to our master formula, since that's equal to 2 times the dot product, and since the dot product is equal to 0, according to our master formula, this has to equal 0. Hence, if this is equal to 0, by bringing these two pieces to the other side, u plus v length squared must be equal to length of u squared plus length of v squared. And that proves the other side. If these are orthogonal, then this is true. Okay, so that gives us the proof of the Pythagorean theorem in vector form. And really, if you think about it, everything hinged on this initial calculation that we did that relates the length of u plus v squared to the lengths of u squared, the lengths of v squared, and this dot product. So we just use this master formula here to prove both sides of this, or both of the implications in our Pythagorean theorem. Okay, I hope you enjoyed that proof. Let's head back to the class notes. Our next and last subsection is entitled Projections. And let's get into this by thinking about the following problem. So let u and v be vectors in Rn, and u is got to be something different from the 0 vector. Find the scalar c such that v minus cu is orthogonal to u. Now I've got a picture of that situation here just so we can kind of get a mental image of what's going on here. So we've got v and u given to us, and what I want to do is I want to find exactly the right scaling of the vector u. So I want to think of this as c times u. So I may, in this picture, I have to shrink the length of u. I have to scale it by something between 0 and 1, scale it back until cu, v minus cu, and v form a right triangle. Now, one way of saying that is that v minus cu is at a right angle or is orthogonal to this vector u. So what we want to do is we want to work out a formula for this scalar c. How would I choose that value of c so that this picture is created? So let's go over to the document camera and see how we would discover the value of c. All right, welcome back to the document camera. Let's work this problem out. But before we solve this problem completely, let me give you an interpretation of what it is that we're doing. So let me add some context to this problem. What I want us to do is I want us to think of the vector u as the ground level, okay? And I want you to think of v as some vector, think of it as like a flagpole that's sticking out of the ground at some angle. Now, let's imagine that the sun is at high noon, so it's sitting up above here. And here are the sun's rays coming down like this. And what's going to happen is the flagpole that's sitting in the ground at this funny angle is going to cast a shadow onto the ground. So let's picture that. So there's the shadow of the vector v that's been cast onto the ground u. And this shadow is going to be a scalar multiple of u. In this case, according to this picture, it's going to be a multiple of u that's positive but less than 1. It's in the same direction as u, but it's shrinking u. But the main thing is this is going to be some multiple of u. Let's call it c times u. And the question is, how would we know what this value of c is? How would we determine it? Well, the key insight is that this residual vector, I'm going to put it in here, in this direction. This residual vector is going to be v minus cu. And it has to satisfy the property that it's at a right angle to the vector u, right? This is going to form a right angle because the sun is directly overhead. So there's going to be a right angle here. And so the condition to finding the value of c is going to be that this vector v minus cu is going to have a dot product with u that's equal to 0. So the condition for c is going to be obtained through this condition. All right, that's a way of saying that v minus cu is orthogonal or at a right angle to u. Now, knowing this and knowing some properties of the dot product, we can now work out the value of c. So we can use the distributive law here. We'll have v dot u minus cu dot u has to equal 0. And now we can use our associative principle to work out u dot u first and then multiply by c. And then finally, we can bring this to the other side and divide by u dot u, or write it this way. We can say that c is equal to v dot u over u dot u. So there's the scalar multiple that we should use. If we use this value of c, we'll create this picture. We'll have a shadow that's cast by v onto u so that this residual vector is at a right angle to the original vector u. All right? Now this vector has a special name because this kind of action of projecting one vector onto another is so important that this has its own name. This is usually called the projection of v onto u. And the important thing here is when we're doing a projection of v onto u, we're going to end up with a vector that's in the direction of u. It's going to be a scalar multiple of u. All right, now what I want to do is I want to go back to the class notes and we'll take up this concept of projection in a little more detail and we'll do a calculation with these projections. So join me back at the class notes to pick this topic up in a little more detail. So here's our definition of a projection. Let u and v be vectors in Rn, u not equal to 0. The projection of v onto u is the vector, and we have to get this notation right. We're going to use the notation PROG for projection. We're going to say this is the projection of v onto u. So the vector that's being projected is always going to appear inside these parentheses, and the vector on which it is being projected will appear here as a subscript. So the projection of v onto u is what? It's a scalar multiple of u, and that scalar takes on the form v dot u over u dot u. Now, u dot u could be rendered as the length of u squared, but this form is a very nice, appealing symmetric form. It's very easy to memorize. It's just v dot u over u dot u. All right, now, just so you get the right idea about projections, let me show you a couple of scenarios, right? In each of these figures, the red vector is being projected onto the green vector. So in this scenario here on the left, we can see that we have to stretch the vector u in order to create the projection. So in fact, the scalar multiple is a number, a positive number bigger than 1. We have to stretch u in order to create the projection. We might also have a situation like this, where the angle between u and v is greater than 90 degrees. In this case, I have to flip u. I have to multiply by a negative scalar in order to create the projection of v onto u. So these are all possible. When we're thinking about projections, we have to allow for a lot of different possibilities of how that picture might look. Now what I want to do, and this will be our last calculation, is take a look at a problem where we take a couple of vectors in R5. So I've got vectors u and v laid out here for you in R5. And I want to find the projection of v onto u. And then I want to find the projection of u onto v. So let's go to the document camera and carry out these calculations and compute some projections. All right, welcome back to the document camera. We're going to do a couple of projection calculations. We're going to project v onto u, and we're going to project u onto v. Now, in order to do that, we're going to need 3 different calculations in total, right? We're going to need to get u dot v, which is the same as v dot u. So let's see. We'll need u dot v or v dot u, however you want to think about it. And that's going to be simply what I get when I do component-wise multiplication and addition. So we're going to get a 1, 0, 0, 0, negative 4. So this is negative 3. That's u dot v. When I do u dot u, which is just the length of u squared, I'm going to get a 1, 0, 4, 16, and 4. So this is going to be 25. And when I do v dot v, I'm going to get 1, 4, 0, 0, 4, which is 9. Now I just need to put these together in the right order, right? So if I want to calculate the projection onto u of the vector v, now what I'm thinking is that this is the vector that's casting the shadow, and it's casting it onto this vector. So we're looking for a multiple of the vector u. So this is going to be some scalar times that vector u. We know that the denominator is going to be the u dot u part, and the numerator is going to be the v dot u part. So we just have to remember how to put all the pieces together. So for this particular projection, we're going to get the negative 3 in the numerator, the 25 in the denominator, and this is a multiple of the vector u. Okay, now if I needed to, I could write out all the components. I could take every one of these components and multiply it through by negative 3 over 25. So I could work out every single component of this vector, but we know what to do from here. Now we also want to find the projection of u onto v. So now we're thinking of this as the vector whose shadow is being cast onto the vector v. And so we know that this is going to be a scalar times the vector v. And in this case, the denominator is v dot v. And the numerator is u dot v. Okay, so it's just a matter of assembling the pieces now. We've got negative 3. This time divided by 9 times the vector v. And again, if I needed to work out the components, I could simply scale these by that negative 3/9. So I'll leave that to the interested viewer if you want to work out all the components of these projections. But the main thing is to get these scalings correct, make sure we get them in the right order, and then if you needed to, you could go through and work out all of the components of the projection. So that brings a close to part B of section 1.2, and that brings a close to section 1.2. So I will catch you next time when we begin a video lecture on section 1.3. Until then, take care.